go to the Radon transform demo that's in the stuff. So this is MATLAB code actually written by hand in the old days. And what it is we have positions in the 2D plane, X and Y positions, which we're putting a value of 1. So that's like a single pixel spot. And then we're going to take those data, take the radon transform of those data to get the GL theta or the sinogram. And then we'll take that sinogram and do the inverse radon transform to go back and see the image. And we'll change some of the variables about the radon transform, and we'll add noise to it. Okay, so let's just, normally what I do is I put if you put one of these, oh, it looks like the whole thing's lit up. So I can run this entire, by putting this double percent sign down here, it just lights up this whole thing. And if you on the Mac, if you just hit Command Return, it'll run all of the code that's yellow there. And so it'll just run this code and pop up all the figures. So if we look at figure 1, which is the original image, there it is. It's got these little dots in places where we put them. And then the parameters of the run are shown over here. So the delta theta for sampling GL theta is 2 degrees. We're going to go through 0 through 180 degrees. The signal to noise is 1.5, so it's pretty low signal to noise. And the reconstruction kernel is the ramp filter or the Rumlock filter. Okay, and so now if we look at GL theta, here is what this 1, 2, 3, 4, 5, 6 points have 6 curves in here. 1, 2, 3, 4, 5, 6. And these are the data with this being theta and this being position on the detector. So this is our GL theta. It's a very simple function. It's 1, or it's not ones, but it's non-zero values along these sinusoids. If we look at the noise-free radon transform, so I put this data into the inverse radon transform and go back to the image, this is what I get. And so is it any different than the original image? Well, here's the original image, right? And here's the noise-free image. And we look and say, is that dot any different? To really look carefully, we should go to the zoom function and like zoom that image up and say, okay, well, that's what that dot looks like. It's got some side bands, right? Whereas this dot over here, right? If I zoom all the way in, it probably is just a single pixel. Indeed, it's a single bright pixel. This one is now perhaps 6 pixels. It could even be, 9 pixels or something, but it's got some kind of spread on it from the inverse radon. So now let's look at, that was the noise-free inverse radon. Here's the raw noise picture. So whenever you're simulating noise, you want to add the noise in your simulation where it occurs. And so in our case, our noise will occur as we're collecting GL theta. So for each theta, we take a measurement, there'll be noise on that measurement. And so here's the noise field that we're going to superimpose on this GL theta data. So this won't be zeros in the background anymore. It'll have random numbers and random noise. And the height of those random numbers in relationship to the height of these curves is given by this ratio here. The data signal to noise ratio is 1.5. So noise-free radon transform looks like that. Raw noise looks like that. GL theta plus noise looks like this. Doesn't look too good, right? Now we can barely see the sinusoids, right, in that noise field, right? So that a signal to noise of 1.5, we really don't have a lot of signal compared to noise. Yeah. And so let's look at this is the inverse radon of this with the noise field. And remarkably, you still see these points here. It's hard to appreciate that they're there. But because they're on a sine wave and you're adding everything up to get this point, you do see it in the final image. And we can zoom in and take a look, at what that looks like. And there it is. It's probably a significantly higher pixel than those surrounding it, right? And let's go back to, okay, so that was the last one. So let's go back and change some stuff. First of all, let's change that signal to noise because that was really tough going. Where do I set the signal to noise? Okay, data peak to noise ratio. Well, let's set that instead. We'll set it to 5. Remember, 5 was the magic number. So 5 sounds like that was the Rose criteria, but that was in space. This is in. So now you can see the noisy data looks like this. And now the inverse radon from noisy projections looks like this, much better. Let's zoom in and we'll see. Now it's got a much more significant height compared to the noise background, right? Now let's try a few other things. Let's look at changing the number of projections. So instead of doing every 2 degrees from 0 to 180 degrees, let's do every 10 degrees and see what that image looks like. We'll go there. It just runs everything again. Okay, so now we see that we have many fewer angles, right? So we probably only have 18 angles, like it's every 10 degrees. So GL theta is not a terribly well sampled function, but we still get some pretty good pictures, except for this streak artifact right down the middle here. And if we zoom in on our single pixel, it's reasonable, right? So let's go think. Can I not go back down? I guess thought I could unzoom this thing. There we go. Well, let's zoom back up to this one. You can see we have this horrendous artifact right down the center, and you can try and explain that if you wish. Okay, so that is undersampling. Another form of undersampling is, let's say, we'll get projections every 2 degrees that seem to work, but let's say we're going to go from 0 to 90 and see what kind of image that makes if we only use 90 degrees. And here we've subsampled so that we cut off the data here. And now we see a new type of artifact in the image, and that the object itself is stretched out. Obviously, you haven't got information in every direction, right? So some directions will be spread out and it'll be quite uncertain in those directions. So that's how you can use this program to play with the signal's noise, play with different sampling criteria. And then one thing we did down here, I think, we didn't do any smoothing there. So we could try smoothing some of the noise. So let's set the noise back to, signal to noise is pretty low, down at 2. Okay, so let's run that and take a look and see what it looks like. So here we see, kind of a noisy picture. So we're going to filter the data. We'll come over here, and instead of just having random numbers, we're going to smooth this data over here and see what it does. And so this filter, let's say smoothing 1, you can put whatever filter you want in here. But this is just a 3x3 box, and it runs over the raw data, and it averages the data. Okay, and it's equal. So it's basically all of the 9 points go into the center point, and it's the average of those 9 points. So let's see what that filter. That's a pretty smoothing filter, right? And that's what it does. Okay, and you can see the fact that we have not sampled 180 degrees. That's some pretty crazy stuff, right? We have information about spatial frequencies in this direction, not so much in this direction, though. And so it adds a couple of artifacts, and the smoothing really amplifies what those artifacts look like. If we go back and say, you know what, let's do the whole 180 degrees, right? And see what that artifact looks like. Okay, so now though we have a symmetrical artifact, but it does look like as we go farther out, we get this crazy repetition of the box, and so it's really stretching that thing out. So obviously something is happening to the large amplitude sine waves that is more severe than that one in the middle. And you can work on that. Okay, so that's just how to play around with the inverse radon transform of data that you have manipulated to represent some change. You could do it with motion, you could do it with signal to noise, you can try different unusual sampling algorithms, etc. Okay, well, have fun with that.